Let's continue on with our discussion of organic chemistry. So page 16, lecture outline book. Previous video, we started this and we built this table. We talked about carbon and hydrogen being the foundation of organic molecules. We listed those that we were going to talk about over the next couple of weeks. If you switch from the lecture outline book for just a few minutes to the packet, the quick guide to the structure of organic molecules. I wanted to fold this in here. We normally, in a regular semester, would have stolen a little bit of lab time to do this, which is why it's not in the lecture outline book. But it's important to do this moving forward before we get into the individual organic molecules. So let's just use this packet for a few minutes and get some concepts out of the way. First, again, just a reminder, to be organic, you're dealing with a molecule that contains carbon atoms and that contains hydrogen atoms. So again, other atoms may or may not be present, but you've got to have at least one carbon and at least one hydrogen to be an organic molecule. So just a few odds and ends about interpreting organic molecules and structures. The first thing you need to know about is carbon itself. Notice that we have not mentioned carbon prior to this discussion. We didn't use carbon as an example any of the times when we drew atoms off the periodic table. There is a reason for that. Carbon is one of only two atoms on the periodic table that doesn't follow those rules about distributing electrons. If you recall, when we were drawing atoms, we said that you should draw electrons out in such a way that you distribute them like this. For example, if I want to draw the valence shell of a sulfur atom, it's got 6 valence electrons. I'm going to go 1, 2, pair the first 2, then 3, 4, 5, put them out singly, and then 6, I pair it up again. Rather than going 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, you pair the first 2 and then put the others out singly until you have to double them up. You remember that from previous work when we drew atoms. Well, there are only 2 atoms on the periodic table that are exceptions to that rule. Carbon is one of them. The other is silicon, and we're never really going to use silicon in this course, but carbon certainly we need to talk about. So if you look at carbon, it's in column 4 of the periodic table, so it clearly has 4 valence electrons. You would think, according to our previous rules, that we're going to go 1, 2, 3, 4. But that's not how carbon works, as I just said. Instead, carbon's electrons are going to be distributed symmetrically or evenly around the carbon. 1, 2, 3, 4, around the nucleus of that carbon. So here's the Lewis dot structure of a carbon atom. Just to highlight these, there's 1, 2, 3, 4 valence electrons, each off by themselves. And think about what that means. If you read this, I'll restate this. When you look at atoms' valence shells, for example, let's look at the Lewis structure of hydrogen and oxygen and nitrogen. The number of valence electrons that are alone, that are off by themselves, that aren't already paired up like these or these, typically indicates the number of electrons that are available to be shared, which translates into the number of covalent bonds that that atom can make. Hydrogen has 1. Hydrogen always makes exactly 1 covalent bond when it bonds to other things. Oxygen, there's a pair of electrons, here's a pair, but there's one by itself, there's one by itself. That one and that one are potential half pairs, so to speak. This one can be shared with some other atom. This one can be shared with some other atom. So oxygen typically makes 2 covalent bonds. Nitrogen, there's 1, 2, 3 electrons in the valence shell off by themselves. So nitrogen typically makes 3 covalent bonds. And I've summarized that in the table down here. You're going to need to know that. I just call these the bonding rules. So when you see carbon and when you look at an organic molecule and carbon is there, expect that the carbon atoms will each be forming exactly 4 covalent bonds, no more, no fewer. Expect that nitrogen will be forming 3. Expect that all the oxygen atoms will be forming 2 each, and all the hydrogens will be forming 1 each. If you're looking at the structure of a molecule and these rules aren't being followed, then something was drawn incorrectly in that structure. So that's what this page is telling us. If you go to the next page, there's a few more items that we need to think about when we talk about organic molecules. And functional groups is at the top of the next page. So what's a functional group? Well, I like to think of a functional group as just a little modular cluster of atoms, maybe 2, 3, 4 atoms. It could be more than that, but typically 2, 3, or 4 atoms stuck together, atoms that like to travel around with each other, atoms that are frequently seen clustered with each other. And because they are so frequently seen together in these defined clusters, they're given names. These are some of the names, and I'll tell you about them in just a second. So let's draw one to help explain this. A hydroxyl group. Oxygen atoms always form exactly 2 covalent bonds. We said that on the previous page. So you know that covalent bonds are drawn as straight lines. Let's draw one and draw another. So there's the 2 bonds that it's going to form. Let's say one of those bonds is being spent on a hydrogen. We're going to bond an oxygen to a hydrogen. There's a covalent bond, a shared pair of electrons between these 2 atoms. You know that hydrogen always forms exactly 1 covalent bond, so it's doing its job. Oxygen forms 2. There's 1. What about this one? Where's this one going? Well, in the case of a functional group, it's not a complete molecule. It's not a finished molecule. It's a group of atoms, and one bond off one of the atoms is going to be left seemingly going nowhere. It's going to be dangling off into space, because that's going to be the bond that's going to allow this oxygen to hold on to some other larger molecule that simply isn't drawn right now. So these atoms travel around together frequently as one modular unit, and they attach to larger structures by means of that one bond there. I'm just not showing you what it's attaching to right now because I'm not trying to draw a whole molecule. I'm just trying to draw what's called a hydroxyl group. It's a hydrogen and an oxygen, hence hydroxyl. And it's a functional group. You may see this very same structure drawn with the letter R over here, a capital R. If you look on the periodic table, you'll notice there is no capital R on there. There's nothing that's symbolized with a capital R. So it's used in these kinds of chemistry circumstances as a placeholder. It's a filler. It says, yes, I know that something eventually has to be linked here, that oxygen has to share an electron with somebody else. I just am not saying who it is right now. I'm just not, I don't want to be that specific right now. So I'll just put an R there as a place filler just to note that, yes, I know something's supposed to be there. So some people will draw a hydroxyl group like this. Some people will simply omit the R and just leave it like that. And for our purposes this semester, either way is fine. Still another way that you may see a hydroxyl group drawn. Hydroxyl groups are so common in biology and in chemistry and in the natural world that it's the one and only time where you can represent a covalent bond without using the straight line. Every other time you want to have a covalent bond appear, you're drawing that straight line there. But over here, everybody knows that there's a covalent bond between that oxygen and that hydrogen. Just draw the OH, and everybody knows that that's there. You're just not drawing it. And as you draw these organic molecules, you'll find there's a lot of hydroxyl groups that appear, and it just saves you the time, and it's less messy to draw it this way than that way. So that's correct. That's correct. They're equally correct. Again, if you want to put the R there, that's an option as well. You don't have to. So any of those 4 ways that I showed you are ways to draw a hydroxyl group. Let's do 2 others. There are many, many different kinds of functional groups. We'll see others this semester. We just need 3 of them for the next week here, for the next batch of material. An amino group. An amino group includes a nitrogen atom, and again, think on the previous page. Nitrogen atoms are capable of forming 3 covalent bonds. Let's draw lines out to set us up for that. There's 3 bonds coming off of there. Hydrogen atoms are capable of forming 1 covalent bond each. So if we put a hydrogen here and say, oh, we got a nitrogen to hydrogen bond, that's legitimate, that's valid, that could happen. Let's put another hydrogen over here. So nitrogen spending 1 of its 3 bonds on this hydrogen, spending another of its 3 bonds on that hydrogen, and because this is a functional group and not a final complete molecule, we have to leave 1 bond open, doing nothing here. So what you see here is an amino group. Again, you could put an R there. You don't have to. Either way, it's a correct way to draw an amino group. You will occasionally see amino groups drawn like this. Rather than drawing the bonds, it is implied that nitrogen is doing this with the hydrogens, and there's really no other way to arrange these three atoms correctly except that way. So this is just kind of a shorthand way to represent that. Either of what you see there is a correct way to draw an amino group. We're going to need to talk about those later on this week in future videos. Finally, there's one more functional group that we need to deal with right away. It's called the carboxylic acid group, or for short, some people call it the carboxyl group. Either way is a correct term. There's a carbon involved there, as you probably can guess. And again, carbon forms 1, 2, 3, 4 covalent bonds. Let's draw the lines out there and see where they're going to go. Let's say that one of those bonds goes to an oxygen, and that oxygen spends its other bond to go to a hydrogen. In other words, we put a hydroxyl group there. It's one of these, and we're going to make it part of an even bigger group. So we've got an OH there, a hydroxyl group, holding onto the carbon via this bond. Let's spend two more of carbon's bonds to a single oxygen atom. Remember, oxygens form two covalent bonds. Well, from this oxygen's perspective, there's one, there's two. I'm done. From this carbon's perspective, I've got enough bonds to spend. I spent one, here's two more, and I still have a fourth one. What you see there right now is a perfectly correct way to draw a carboxyl group, or a carboxylic acid group. Again, leave one of the bonds dangling off into space. That's the one that's going to help this thing latch onto some bigger molecule. You will see what we mean by that later on this week. If you want to put an R there, you can. You don't have to. And then finally, there's still another way to draw this, again, kind of a shorthand way. I can say, well, we've got the carbon, and there's two oxygens and a hydrogen. What if we just do this? That's a way to draw a carboxyl group, because there's, again, really no other way to arrange these things properly except the way you see here. So this implies that structure. It's just easier to type this in a line of text than to try to draw it out like that. So that's a good way to draw this as well. So there's three functional groups that we're going to need in the immediate future, and again, we're going to draw more as we move further into this chemistry and this organic and biochemistry portion of the course. So that's functional groups for today. Okay, if I were you right now, I would pause this video. I would go back and review what we've done so far. Make sure you understand what a functional group is. Make sure you understand which atoms form how many bonds. We've got carbons, hydrogens, oxygens, and nitrogens that are going to be in play for this discussion. Just review the first page and a half of this packet. And so, hit pause, feel free to do that. Okay, moving on, now that you've paused and reviewed, let's take a look at the last portion of this packet here. Chemical formulas and molecular weights. We got to know how to do some basic chemistry here, how to refer to molecules, how to know how much they weigh, some good basic chemistry skills that we're going to do right now. So first of all, a chemical formula tells you which atoms are present in a particular molecule. And it also tells you how many of each atom are present. It's almost like the recipe for a particular molecule. I've given you one example here. If you look at a water molecule, and we certainly have talked about water, we discussed water back when we did hydrogen bonding and polar covalent bonding, for example. If you remember, we had models even of water. We said there's an oxygen, there's two hydrogens, and there's a covalent bond here, and there's a covalent bond there. If I wanted to write the parts list, so to speak, for a water molecule, I'd say, well, there's two hydrogens and there's one oxygen. That gives me the formula H2O right there. The subscript after the H, the 2, means that there are two of them. You don't put a 1 after the O. The 1 is implied if there's no number there. So there's a chemical formula for water. Pretty straightforward. You can do that for any structure you happen to be able to draw. The weight of a molecule is also important to be able to calculate. We'll call it the molecular weight or the molecular mass, or what some people call the formula weight, because we're going to use a formula to determine it. I've used water again as an example here in this paragraph. I said, well, if water is made of one oxygen atom and two hydrogen atoms, and oxygen atoms weigh 16 AMU each. How do I know that? I looked it up on the periodic table. Hydrogen atoms weigh 1 AMU each. I also looked that up on the periodic table. So 16 plus 1 is 18. This molecule weighs 18 AMU. Always use the unit of measure. If I say this weighs 18, I didn't give you any information at all. It was useless to say that weighs 18, because 18 pounds, 18 tons, 18 ounces, 18 what? I tell you this weighs 18 AMU, and I've given you the molecular weight or formula weight of a water molecule. So that's described as an example right here. And again, please don't forget to include units of measure when you express molecular weights. Just as practice, let's try a couple of these. Let's do formaldehyde. That's a molecule of formaldehyde. You may or may not be familiar with, what formaldehyde is used in. We'll actually talk about it later this semester. But let's take a look at, first of all, what its chemical formula should be. Well, there's one carbon, there's two hydrogens, there's one oxygen. So carbon, I don't write the 1, it's implied. There's two hydrogens, I put the 2. There's one oxygen. That's the chemical formula for formaldehyde. It's that easy. Just count everything up, write them, and if there's more than one, put the number down there as a subscript. So a lot of times people say, well, what if I wrote H2CO or OCH2? It's not wrong to do it the other way. Usually it's conventional for an organic molecule to write the carbons first, then the hydrogens, then other stuff, in this case just the oxygen. It's not a strict rule, but more often than not, you'll see the carbons written first, then the hydrogens, then other stuff. So I'll write it out that way. That's a chemical formula for that formaldehyde molecule. Now, how much does one of these weigh? What's the molecular weight or the formula weight of formaldehyde? All I have to do is have a periodic table handy and say, well, what's my formula? I've got one atom of carbon, I've got 2 atoms of hydrogen, and I've got 1 atom of oxygen. If I have my periodic table handy, I can look up the weight of each of these atoms. I will find that carbon weighs 12 AMU, hydrogen weighs 1 AMU each, and oxygen weighs 16 AMU. So I multiply. 1 times 12 is 12. 2 times 1 is 2. 1 times 16 is 16. And I add it all up. If I add all this up, this adds up to 30 AMU. Right? These were AMUs that I had here. I add them all up. I got AMUs. So the molecular weight, or formula weight if you prefer, of the molecule formaldehyde is 30 AMU. That's how to do a molecular weight. You got a structure, you can figure out the formula, you can figure out the weight. Or if you have the formula, you can figure out the weight directly from it. That's all you got to do is add stuff up and multiply by the weight of each atom. Okay? So, again, I would recommend pausing here. Rather than chopping this packet up into 3 separate videos, I'm just going to stop, recommend that you pause, verify that you understand this, and then start the video again. And let's do that. So on the next page, you can see all the stains on this is an antique desk, and it's messy, but I like it. So there we go. This is page 3. This is kind of an extension of what we did on page 2 of this packet, talking about these shapes. So I'm going to use the marker board to highlight this, and then we'll come back to the paper. It's very common in biochemistry and organic chemistry and lots of things that we're going to do this semester and in all sorts of semesters in a biology course. It's very common to see what look like hexagons and pentagons and these weird geometric shapes as parts of molecules. And so if I show you this and I say, hey, that's a structure of a molecule, you're going to say, all right, I see a nitrogen and 2 hydrogens, but what exactly is that? And what does that have to do with anything on the periodic table? It's really, really important to be able to answer that question. In other words, to know what that thing there means. Right now, it just looks like a hexagon. And so let's break that down. I'm going to redraw that molecule just so I can draw and erase and redraw here. So here's the molecule that you see on page 3 of this packet. There's an amino group right there, right? That's an amino group. And then there's this thing, this six-sided, six-cornered figure. Well, think about what we're doing. We're trying to draw organic molecules. And as you know, organic molecules always contain carbons and hydrogens. Well, if you're drawing big, complicated organic molecules, you're going to have a lot of carbons and a lot of hydrogens. And if you want to draw it out, it's going to take you all day to draw all the letter C and all the letter H's over and over and over again. It would be nice if there were a shortcut for that, an easier, quicker way to represent carbon atoms or hydrogen atoms. That's what that six-sided figure right there is an example of. Every time you see one of these geometric shapes, I'll call it, every corner, right there, for example, or right there, right there, right there, right there, right there. Every corner or every angle, if you prefer to say it that way, represents a carbon atom. So I didn't write the letter C 1, 2, 3, 4, 5, 6 times. It saved me all that trouble and all that messiness on the paper here. But it's implied. If I know how to interpret this structure, I know there's a carbon atom here, 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 and here. Just for purposes of this explanation, I'm going to write the letter C in there, even though I wouldn't actually do that. It would defeat the whole purpose. It's going to make it really messy. But for this illustration, I'm going to write the letter C in there to represent those carbon atoms. Okay, think about what you already know about carbon atoms. Carbon atoms always form exactly 4 covalent bonds. Well, in this drawing, straight lines represent covalent bonds, including that one, and 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 that one. These are just covalent bonds. So from, say, here to here, there's a covalent bond between this carbon and that carbon. From here to here, covalent bond between that carbon, and so on. But if you think about it, there seems to be a problem. If that's a carbon atom, it's using 1, 2 of its covalent bonds. What about the other 2? It has to spend all 4 bonds. Right now, I only see 2 of them in play. If that's the case, and nothing else is drawn here, it is understood, it is implied, that the remaining available bonds are going to hydrogen atoms. Because again, hydrogens and carbons are the basis of organic molecules. So the default is, if I'm not showing you what it's bound to, assume it's bound to hydrogen. So what I just wrote in green here, again, isn't something I would actually draw in this picture. I'm doing it for purposes of this explanation, because we're going to go back and count in a couple of minutes. But if I look at this particular carbon, I say, okay, now 1, 2, 3, 4, it's making 4 bonds. That's what it's supposed to do. Let's do that to each of these carbons. Let's look at every single corner and make sure that it's making 4 bonds. Here's a carbon. 1, 2, I need 2 more, so 3, 4. Here's a carbon. 1 bond, 2 bonds, we'll give it 2 more. 3, 4. Here's a carbon. 1, 2, 3, 4. 1, 2, 3, 4. There's a carbon. 1, 2, 3. It only needs 1 more. So now if I go back and review, see how messy this got. This is why we use the simpler notation, so we don't have to draw all this stuff out every day. But if you go back and review what we've got, every single corner in there represents a carbon atom. 1, 2, 3, 4, 5, 6. Every single carbon atom should have exactly 4 bonds coming off of it. 1, 2, 3, 4, 1, 2, 3, 4, etc. So all I did was I gave every carbon hydrogens until it had a total of 4 bonds that I could see. Now, if I want to know the formula of this molecule, I go back and add everything up. Let's start with the carbons. There's 6 of them. C6. Let's take a look at the hydrogens. I'm going to put a little slash through them so I don't lose track. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. H13. And is there anything else besides carbons and hydrogens? Yes, there's that 1 nitrogen atom, so we'll write N. That's the formula for that molecule. But think about how messy it is if we draw every single carbon and every single hydrogen out. It's horrible to look at that and interpret it. I could just as correctly draw it that way and it's a lot easier to look at, it's a lot faster to draw, and anybody that understands this concept knows that this means that. It's just a lot neater and takes up a lot less space. So this molecule right here has, as we said, a chemical formula of C6H13N. If you want to know its weight, all you have to do is multiply. I've got 6 carbon atoms. Here's my carbon atoms. I've got 6 of them, and they weigh 12 AMU each. I've got some hydrogens. Specifically, I have 13 of them, and they weigh 1 AMU each. I've got a nitrogen. There's 1 of them, and it weighs 14 AMU. So do the math. 6 times 12 is 72. 13 times 1 is 13. And 1 times 14 is 14. If I add these up, let's see if I can do this in my head, I get 99. So the molecular weight of that molecule is 99 AMU. Double check my math here. Yeah, it looks like I did it right. Okay, so that's 99 AMU. That's a whole lot easier to draw and a whole lot less messy than drawing that. However, if you need to figure out the formula weight of that thing and you're not sure, at some point you'll be able to do this in your head. But for now, I recommend going ahead and drawing the hydrogens in there and drawing the carbons in there and adding it up. If you had a problem like this on a quiz, let's say, where it says, what's the chemical formula of that? What's the molecular? And you will have problems like that. No big surprise there. Go ahead and take a piece of scrap paper and draw them out instead of trying to do it in your head. It's just less likely that you'll make an error. Okay. Let's try one more. Below is a molecule. That molecule is called phenol. You may be familiar with it. It's in, if you've ever used Campho-Phenique, which is a stuff you buy in the drugstore. If you have like a toothache pain, that's in there. If you have those sore throat lozenges that taste like chemicals that make your throat numb, that's phenol that's in there. Anyway, it's a commonly used chemical in medicine and in industrial uses. Anyhow, that's phenol. Let's take a look at its structure. It's right there, but I'm going to redraw it. Let's try to figure out its chemical formula and its formula weight. I'm going to use the marker board again to do that. So we've got a 6-sided figure, and we've got a hydroxyl group coming off of here, and we've got, notice that there's 2 bonds and 1 bond, and 2 bonds and 1 bond, and 2 bonds and 1 bond. So every other corner has a double bond, like that. So all I did there was just redraw what's on the page, on page 3 of this packet. Let's break this down. First thing I'll do is fill in the carbons. I'll just write the letter C on every corner so I don't forget. Carbon, 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 carbon. Or you can put a little dot there, whatever is easiest for you. Let's use a dot. You could do it that way. Whatever makes this most makes the most visual sense to you. So wherever there's a red dot or the red letter C, that's a carbon atom. Let's figure out if there are hydrogens attached to this thing. We've got, let's start somewhere. Let's start at that carbon. That carbon, from what I can see right now, is making 1, 2, 3 covalent bonds. It's making 2 bonds to this carbon and 1 to there. I only see 3. It's supposed to be making 4. So there must be, implicitly, a hydrogen there on which the 4th bond is being spent. This carbon, I see 1, 2, 3. There must be a 4th. There's a carbon. 1, 2, 3 bonds. I'm going to give it a 4th. It's going to go to a hydrogen. That carbon, 1, 2, 3, 4. It's using all 4 of its bonds. I don't have to give it anything else. It's all set the way it is. Here's a carbon. 1, 2, 3. I'm going to give it a 4th bond to a hydrogen. There's a carbon. 1, 2, 3. Give it a 4th. So what I did is, in red, I put little dots on there that represent carbon atoms. In green, I wrote hydrogens that were implied but not written in the original structure. Now go back and add them all up. The carbons, there's 1, 2, 3, 4, 5, 6. C6. The hydrogens, 1, 2, 3, 4, 5. Don't forget that one, 6. Anything else there besides carbons and hydrogens? And yes, there's one oxygen. So there's an oxygen atom. That is the chemical formula for this phenol molecule. Again, if you want to look it up and read about phenol, that's phenol. So let's translate that onto the paper. C6H6O. There you go. Get that a little clearer. Okay. So what's its formula weight or its molecular weight? Again, just break out your periodic table. You'll always have a periodic table available on exams and any other thing that you're doing in science. Just look it up. So we've got carbon atoms. There are 6 of them. We got hydrogen atoms. There are 6 of them. And we have 1 oxygen atom. How much do carbons weigh? 12 AMU. It says so on the periodic table. How much do hydrogens weigh? 1 AMU each. Oxygens weigh 16 AMU each. So, oops, there's one of them, sorry. 1 oxygen atom. 6 times 12 is 72. 6 times 1 is 6. 1 times 16 is 16. I'm going to add all this up. I get 94. That means 1 molecule of this substance weighs 94 AMU. Double check my math. I didn't use a calculator. You should use a calculator, but or you should use scrap paper and double check it. Check it 2 or 3 times just to be sure. So 12, 14, and that's 94. Okay, good. Always check your answer, you know, and always make sure you got your unit of measure. There you go. So now you can do formula weights, you can do formulas, and most importantly, as far as this page is concerned, you can interpret what these otherwise strange-looking geometric structures look like. If you see these all the time in what we'll be doing this semester and in future biology semesters, and certainly if you take chemistry, you'll see it there as well. But even in everyday life, if you, let's say you get a prescription from the pharmacy, they always put those long pages and pages of drug information in the bag when you walk out of the pharmacy, and it's a tiny little print in there, but somewhere in there they're going to show you a picture of the structure of the molecule that's in that pill that you're taking. And very often you'll see these kinds of multi-sided rings or maybe multiple ones of these. And you're going to say, well, what does that mean? Well, it just is the structure. It's the molecular structure, and they're using this shorthand notation instead of using the complicated, long, messy notation like that. So, keep your eyes open for things like that. That's just one example of where you'll see chemical structures on a kind of a daily basis is, like I said, just look up the information about some prescription that you might take, or even just, Tylenol is called acetaminophen. Google the word acetaminophen, and you'll see the structure, and it's going to have rings in it like this, and you can now interpret that. It's a really important skill to have, and so that's why we're getting it out of the way now. I've left a couple others down here for you to try. Please do so. Please follow up with questions about them. I'll eventually post the answers, but I want everybody to get a chance to try them first, and I can give you more practice problems on top of that if you would like. As I said, I promise you that you will see questions just like this with different molecules on quizzes and exams going forward, because it's just a basic fundamental skill that everybody should have coming out of intro bio like this. It will save you lots of time and aggravation in the future when you're reading biology books and chemistry books and trying to interpret things. So that's that packet. Again, please review it as necessary. Please write down questions and let me know if you have anything that I can help you out with. The next video is going to be about proteins specifically. So we're finally getting into that list of 4 different organic molecules. We're going to start with proteins and go from there, if you recall, page 16. So we're going to be back to the lecture outline book for the rest of the videos in this section.